So, friends, welcome to the lecture number 25, which is continuation of the previous lecture in unsymmetrical melding. These are lectures in module 2 titled Advanced Structural Analysis under NPTEL course titled Offshore Structures under Special Loads including Fire Resistance. We have already understood and we are solving an example in between. We are interested to find the bending stress for a section which is subjected to unsymmetric bending. So, we said that stress at any point is given by minus mu iu v minus mv iv u we said for this being the z axis and these being u and v axis as located at alpha 1 using right hand screw rule, we said that the moment will be mz, which is now resolved as mu, which is mz cos alpha 1 positive, and mv when it resolves it is in the opposite direction, whereas for mu the moment is marked this way and mv is marked this way, but it is resolved in the opposite quadrant, therefore, minus mz sin alpha 1, which we said this is 4 cos 70.36, which amounts to plus 1.344 kilonewton meter, and this is minus 4 sin 70.36 degrees, which is 3.767 kilonewton meter. So, substituting sigma x will be set to 0 for locating the neutral axis, because in neutral axis the stress value is going to be 0. So, setting equation 1 to 0, we can say mu by iu into v is minus mv iv into u is set to 0. So, 1.344 by iu 1.575 into v minus mv is negative. So, minus 10 power 6 by 10.457 10 power 4 of u is set to 0, which shows that v by u will be minus 0.422. So, which we say is actually equal to tan beta, where beta is the angle between the positive principal axis uu with the neutral axis. So, beta is the inclination between uu axis and neutral axis. which says that beta is actually equal to minus 22.88 degrees. So, try to plot this. Neutral axis now is going to be minus. So, that is the neutral axis, which is neutral axis, and minus, therefore, we plot this angle as 22.88 degrees. Having located the neutral axis, let us now get the section back and mark all these axes to find the stresses. So, this is the given section. We have the z axis located here and y axis located here, UU axis located 70 degree, this angle is 70.36. We also located the neutral axis, which is 22.88 degrees. So, if you want to really find out the stress at this point, let us say this point A, I must know the distance of this from the neutral axis measured along V. If you want to locate the stress at this point B, I must know the distance of this point measured from the neutral axis, which I call as V B. Obviously, for the given section subjected to a load upward of P, the section is going to bend this way. So, the top members will be in compression, bottom are in tension. So, it is expected that point A will be compressive. And V A will give me the maximum distance of this fiber, and point B will be tensile, and V B will give me the maximum distance of this. So, our job is to now find for A and B the coordinates. One may wonder, A and B coordinates are known to us in terms of the dimensions we are marking now. These are all given to us, but we need to find these A and B coordinates in terms of U and V, because we are going to measure the stresses or the distance of fiber from the neutral axis. So, we have converted the classical unsymmetric bending problem. 2. Uniplanar bending problem, where I can now use the classical flexural equations. That is the advantage. So, I need to find u a, which will be z cos alpha plus y sin alpha. We already derived this equation earlier. Let us substitute the values of, we need the distances already known to us. So, z is minus 7.5 cos 70.36 plus y is measured positive. So, 17.5 multiplied by sin 70.36, which I get as 13.96 millimeter. V a minus z sin alpha plus y cos alpha, which will be minus of minus 7.5 sin 70.36 plus 17.5 cos 70.36, which gives me 12.95 millimeter. So, for the point A, I got the coordinates in terms of u and v axis. I can now find the stress at A. So, stress at A is now minus mu by Iu into V A plus mv by IV into U A. Let us substitute this. One can see here MUV is negative for the given problem. So, I get the stress as minus 0.8 Newton per mm square. Negative indicates it is compression, which is also inferred by us earlier. Let us try to find similarly for point B. So, U B z cos alpha plus y sin alpha, which will be minus 2.5 cos 70.36. You can see here this is the point we are looking at, it is going to be plus 2.5 cos 70.36 plus minus 50 minus 17.5 of sin 70.36. Similarly, V B can be computed as minus sin alpha plus y cos alpha. So, minus 2.5 sin 70.36 plus minus 50 minus 17.5 cos 70.36 So, sigma b can be computed by substitution. So, I want you to do this and check, you will get tensile stresses at the bottom. So, interestingly, the problem of unsymmetrical bending is converted to simple uniplanar bending by locating the principal axis of inertia and the neutral axis and measuring the distances of extreme fibers from the neutral axis and then using the conventional flexural theory. To answer a very interesting question which generally people have intuition to ask, what would be the consequence of unsymmetric bending in design? The answer is very simple. If your cross section is under stresses magnified. To understand this, we will take an example. Let us say example 3. ISMB 500 at 86.9 kg per meter is used as a supporting member of an offshore deck. This section is subjected to a moment m on a plane which is not matching with the axis of symmetry, but making an angle of 2 degrees inclination to the vertical. Plane of symmetry. So, locate the neutral axis, determine the stresses and compare this with symmetric bending. That is the issue. So, essentially there is an I section which has got 2 axes of symmetry, y axis and z axis. It is ISMB 500. The properties are given in the steel tables. It says that the loading is acting on a plane which is just 2 degrees to the vertical plane of symmetry, and the moment is acting about this. We need to find the stresses. Obviously, we need to know the maximum value. Let us compare this at point A and see what is the difference in the stress. For a given section ISMB 500 at 86.9 kg per meter, IZ is given 45 to 18.3, IY is 1369.8 10 power 4, ZY planes or axis of symmetry, since IZY is 0, they are also principal planes of symmetry. MU I want to resolve, which is M cos 2 degrees, and MV is minus M sin 2 degrees. So, now we have the properties of the section, we have the moments, let us find the stress. At point A. The point A is located here. So, sigma A is minus mu by IU into V plus mv by IV into U. I can now straight away say it is minus is because of this value. So, M cos 2 degrees, that is the M value, that is mu, and IU is as same as IZ because they are principal axis of inertia, 218.3 10 power 4. Let us assume that M is in Newton millimeter and V is 250 because this section is 500 and this distance is 180. So, from the CG it is going to be positive 250 plus mv is minus m sin 2 degrees by iv, that is iy, 1369.8 10 power 4, and u is minus 90, which makes this equation as m of minus 0.55 10 power minus 11 plus 0.23 10 power minus 11, which makes 0.32 m into 10 power minus 11 Newton per mm square. Let us now consider sigma A dash, that is no inclined load. Which is simply m by I into y, which I can say m by 45218.3 10 power 4 into 250. That is, instead of the load acting at an inclination, the load acts vertical. Okay. So, I get this as minus 0.55 m 10 power minus 11 Newton per mm square. So, there is a percentage increase because of the inclined load as 0.55 minus 0.32 by 0.55 into 100, which is about 41.8%. So, even in the case of symmetrical axis sections, when the load is not acting on the plane of symmetry, it causes unsymmetrical bending, which enhances the stress by about 40%. Now, let us locate the neutral axis for this problem. We know to locate neutral axis, we need to equate the stress to 0. So, let us say sigma x is minus I u into V plus m v by I u into u, set it to 0. So, minus m cos 2 degrees by 45 to 18.3 10 power 4 into V plus minus m sin 2 degrees by 1369.8 10 power 4 into u, set it to 0 to locate the neutral axis, which tells me by simplifying V by u comes to, let us say m goes away, V by u comes to, let us say, okay, this is negative, this is also negative, this stays here, okay, which comes to minus 1.153, which we say as tan beta. So, which says beta is minus 49.06 degrees. So, locating back in the figure, we can mark the neutral axis as at an angle 49.6 degrees. So, for the given load, point A is above the neutral axis. So, this will cause compression. So, point A will experience compressive stresses. So, friends, to summarize, when the load does not act on the plane of symmetry, then the section will be under unsymmetric bending. Under this case, stresses are enhanced by significant amount. To solve the problem, convert the problem to uniplanar bending by locating the principal axis, find alpha 1, then locate neutral axis by finding beta 1, then find stresses. So, which we explain with couple of examples. Thank you.